So what I have here is a hermetic compressor. I'm going to show you guys today how to use a multimeter to troubleshoot compressor issues. All right, so what you guys see here is your typical Y arrangement that represents windings in motors that you would see on schematics. Now what I want you to do here is take note of the actual physical structure here. So when you have start and run windings here, and you can see how they meet at a common point right here in the middle. So physically, if I did a continuity reading between run and common, I will always have a closed circuit between those two because there's no switches, there's nothing to interrupt that. The only way I wouldn't get a reading between these 2 points, these 2 pins here, is if I have like an actual break in the winding. Now you can see after these 2 windings, these 2 different circuits meet together, they have to go through the thermal overload here before it gets to that common pin where we're using a multimeter to test. So if this switch is open and there's no connection there, I will get a reading between start and run, but I will not get any readings between run and common or start and common. This is important to understand to make sense. So the first thing I want to show you is how to identify which pin is which with your multimeter in the event you don't have anything that tells you otherwise. So what we're going to do is we're going to take our probes, we're going to put our multimeter in the ohm setting, not kilo ohms or mega ohms, just regular ohms. We're reading single, double digit numbers here, nothing crazy. And what we're going to do is we're going to start randomly testing any 2 pins in different combinations. So if I go from this pin to this top pin here, you can see I'm reading about just under 12 ohms. If I go from that top pin to this pin over here, I'm reading about 5.5. And if I go to these 2 pins here together, I'm reading much larger number, almost 17 ohms. Once you identify the largest number that the 2 pins give you, that is your start and your run winding combined. So the third one is going to be your common. So these 2 bottom pins here give me 17. That's my largest reading. That top pin there is my common terminal. Now you notice if I go from this pin to my common, I'm reading just under 12. And if I go from this pin to common, I'm reading about 6. So I should read about 17 between these other 2 pins here. And there you have it. So your run and common, start and common will equal start to run. So we know this top pin here, that is our common, but how we know which one is run and start? The run winding is always going to give you the lower value of the 2. So if I test this pin to common, see I'm reading about 5.5 ohms there. And if I go from this pin to common, I have a larger reading, almost 12 ohms there. So that smaller one is going to be my run winding. So that is my common, that is my run, and that leaves this one as my start winding. Now a really stupid, easy way to remember that relationship is just the number of letters in the word themselves. Run has only 3 letters, start has 5 letters, 3 is smaller than 5. So the smaller number is your run, higher number is your start. So what I'm going to do now is we're going to simulate bad readings on a compressor. So first thing I'm going to do that, so I'm going to take these alligator clips, I'm going to put it on my run winding, and I'm going to ground it to the casing of the compressor itself. So what I have here is a grounded run winding. Now take notice, if I still do resistance readings, I'm not going to see any changes. So if I go from start to run, you can see I'm still reading 17. From start to common, reading just under 12. From run to common, still reading 5. So everything still checks out, even though it's grounded. So in order to test for grounds, you have to do a continuity test. So we're going to change our multimeter to continuity. That's our beep. And what we're going to do is you can either test to the copper or the metal shell itself. If you go to the shell, you want to scratch some of that paint off and get down to the metal. So we'll take one probe, we'll put it on our run winding, take the other one to the metal of the compressor itself, and you can see I have continuity there. But because of our structure here, we're going to have continuity on any one of these pins we test, because as we stated earlier, run and start windings are connected together. So if that run is grounded, so is the start. The common will also be grounded as long as that thermal overload switch is closed. Now in a situation when you have a ground, you're never going to have an open thermal overload switch because that's going to trip a breaker right away. The compressor's not going to have a chance to actually run and heat up. But if it did, you would have an open thermal overload switch, and the only one that wouldn't be grounded is that common terminal because it's disconnected from the grounded windings themselves. But the run and start are always connected. What I'm going to do now is I'm going to simulate a short between windings themselves, but not to ground. So we're going to go back to our ohm reading. Now when these windings are shorted together, as you would expect when you take a resistance reading between start and run, you're going to get a very low value. There's very little resistance there. But what also changes is your readings between start and common and run and common. So I'm going from start to common here. You could see I'm reading much lower than I did before. Before, on a good compressor, I was reading nearly 12 ohms. Now I'm reading only 4. From run to common, I'm having the same issue. I'm having a lower reading between run and common, where before I had nearly 6, now I'm down just below 4 again. So you could see how my start to common and run to common resistance readings are almost identical, and nothing's adding up. And this is a classic sign of windings shorted together, but not to ground. What I'm going to do now is I'm going to simulate the readings on an open thermal overload switch. So what I have here, this is a little flame rollout switch I pulled out of a furnace that is going to take the place of a thermal overload that's located inside the compressor here. And so what I have here is an alligator clip coming off that common terminal. It's going to my thermal overload switch. And then I have another alligator clip coming off the other side of that clip. And this is going to represent the common pin that we would test off of with our multimeter. So if I put one probe on this common here, now I'm going to take my other probe. Let's do start to common. You can see we're reading our 12 ohms. So what I'm going to do now is I'm going to take this lighter and I'm going to heat up this switch. That's going to open the switch, and you can see we lost our reading between start and common. We should also lose our reading between run and common as well. However, we're still going to have a reading between start and run because those windings are still connected to one another. Now these thermal overloads, once they cool down, they're going to reclose the switch and we'll get our readings back between start and common and run and common. So you heard the switch just close. We now have our 12 ohms returned between start and common, and run and common is also going to give us our resistance values back.